I'm here holding a piece of aluminum 5083. This type of aluminum alloy has been used for years in marine applications due to its remarkable corrosion resistance to seawater. Traditionally, it has been relatively soft, so its use in high-load engineering structures has been limited. This piece of aluminum 5083, however, is special. In a collaboration work with Professor Lavernia and Dr. Topping at UC Davis, we have engineered the microstructure of this aluminum alloy to improve its strength and toughness, creating an ultra-fine grain aluminum-based composite material. The grain size reduction was done by a modified ball milling technique under cryogenic temperature called the cryomilling. The severe plastic deformation during milling breaks the grains into nanosize, and the low temperature prevents grain growth. To see the microstructure that gives this material its unique properties, the surface of a sample must be incredibly smooth. This sample had to be polished using progressively finer abrasives, starting with the sandpaper and ending with silicon colloidal suspension liquid. Here you can see a mirror-like finish on a microscope-ready sample. Because the grains of these materials are only a couple hundred nanometers, ordinary light microscope cannot resolve the features that we are interested in. Fortunately, we have access to electron microscopes here at USC, which have the resolution on the order of several nanometers. Through this scanning electron microscope, we can see two distinct areas in our sample. The bright area is the coarse grain regions which contribute to the ductility of this material. The dark area is the ultrafine grain region reinforced with boron carbide, the hardest material in nature after diamond and the cubic boron nitride. This region gives it extraordinarily high strength compared to conventional aluminum alloys. To learn about the deformation and the failure modes of this material, we want to watch it under the scanning electron microscope while running an in-situ microtensile test. Miniature tensile specimens are loaded into the microtensile testing stage, then placed into the SCM vacuum chamber for imaging throughout the deformation and the failure process. We can use digital image correlation software to evaluate these images to track the evolution of microstrain and the formation of microvoids. Using this technique, we can also see how cracks propagate, frequently through this heterogeneous microstructure. The data we have collected indicates a significant improvement on strength and toughness in these aluminum nanocomposites. Future work includes finding the best fabrication parameters and making this material more ductile. We hope that by addressing these issues, someday this material may be incorporated in many high-performance, weight-critical applications.